Hello everyone, hope you are doing well. Welcome to the online platform Civil Technobricks. Guys, here we will tune for instantaneous decoding of conceptual knowledge in the field of civil engineering where study elaborates decoding the earth to build a better world. Today we will go through the core concepts of one of the geohazards like floods, causes, mitigation and prevention in view of civil engineering. To understand, flood is defined as a temporary condition of partial complete inundation of normally dry land. So floods as a critical hydraulic and hydrological geohazard that required a system engineering approach to evaluate risk. The lecture focuses on examining the underlying physics of inundation and assessing the core structural resilience of civil infrastructure. At flood geohazard management must move past emergency response toward an established hierarchy of proactive control measures. So we have to provide proactive control measures to prevent the actual disaster impact. Understanding these mechanics is essential for minimizing catastrophic economic losses and prioritizing public safety in hazardous zones. So geohazard trigger when the hydrologic discharge directly surpasses the natural or artificial conveyance capacity, just like rivers, of the drainage channels. From the geotechnical engineering point of view, submerged infrastructure experiences intense multi-directional stress which caused by escalating hydrostatic pressure. Floodwaters exert massive lateral thrust forces against retaining structures which can induce structural overturning or catastrophic wall failure in picture. So flood zone and the flood stage. We have to study the definition of flood event where capacity exceedance of the actual natural discharge just like rivers or the channels. So with reference to the engineering context, hydrostatic pressure, which is the most important phenomenon, which is acting the pressure laterally where water exerts multi-directional stresses on submerged bodies. With reference to that, 1 mile depth is equal to 2346 psi. So flood waters exerts massive lateral thrust against retaining walls. So we have to provide the retaining walls with sustainable forces. Here classification of the flood by the mechanism and onset. So three floods: riverine floods, flash floods, coastal floods. Riverine floods where the graphical representation with reference to the duration to the discharge. So time and discharge. As time increases, discharge increases. Extensive duration and slow onset. So slow onset is the slow onset. At the initial phase, there will be a slow onset, but at the end, where extensive duration is there, driven by prolonged precipitation across large catchments. Where flash floods, where the graphical representation, the graph is initially rapid onset below to the 6 hours, where high velocity is there. Rapid onset, high velocity, driven by high intensity rain in steep and urban catchments. And at the third, coastal floods, where storm surge, tides, and tsunamis are occurred with reference to the coastal region. So the critical metric is that, or the flood classification is dependent on the time of concentration (TC), the time required for runoff to travel from the most remote point of the watershed to the outlet. Most remote point of the watershed to the outlet. So three basically types self explain that the time and the discharge, or the relationship between the time with reference to the discharge. The critical metric flash flood severity is dependent on the time of concentration, where duration required for runoff to travel from the furthest point of watershed to its the outlet. Owing towards the flood etiology, where input versus physical constraint is explained, the manifestation of a flood geohazard dependent on the meteorological, physical and geological and discharge. So meteorological characteristics are the input, Physical and geological characteristics are the system constraint, and flood discharge is the output. So, with reference to the meteorological characteristics, heavy rainfall, snowfall, cyclones, they are the input for studying the ecology. In the process, the physical and geological system constraints, just like characteristics of topography, slope, gradient, failure in the dam, channel obstruction, these are all the geological and physical constraints which are dependent on the meteorological characteristics, which gives the output as a flow deviation, or we can say that the flood discharge. So in the image, with reference to the geological context, channels or the natural streams travels or collect the water from the nearby watershed. If heavy rainfall occurred in less interval of time, then a huge flood will occur, and that whole water is accumulated within the natural streams. But if rainfall is continuous and rapid, then that channel can't consume the whole runoff, and that time we get flood situation. Now urban flooding, where the anthropogenic factor. So why urban flooding we have to study? Urban flooding is calculated by using the rational method, where discharge Q is equal to CIA. What do you mean by C? C is the runoff coefficient. What do you mean by Q, which is the peak discharge? What do you mean by A, which is the area? So now if we are calculating the discharge with reference to the rational method, so we have to study the natural basin, urban basin, natural basin which is a part of tree, which is a part of slopes, which is a part of channel, which is a part of river, where C is equal to 0.2, high infiltration, because land parcel is open to the earth, open to the sky, where water have penetration activity, percolation activity, or seepage. At the second part, urban basin, there are large amount of area is constructed or covered with reference to the concrete. So or concrete, or we can say that road surface. So very few area is available for the penetration of water. So where C is runoff coefficient is 0.9, where impervious surface. So the graphical representation shows that time on x-axis, discharge on y-axis. So the graphical representation with reference to the time and discharge, impervious surfaces drastically shorten lag time and increase peak discharge. So high peak discharge and low peak discharge. So low peak discharge in the urban basin and high peak discharge in the natural basin. Likewise. Now infrastructure vulnerabilities, or we can say that the forces and material degradation. So the mechanical forces and material weakening. Mechanical forces, just like we can say that flood geohazard damage civil infrastructure through two primary pathways: destructive mechanical forces and severe material weakening. So flood geohazard damages with reference to two types basically. So hydrodynamic pressure or score hole, or second part buoyancy uplift, that is the uplift acting forces. Flowing waters apply intense hydrodynamic pressure on the bridge piers, scoring out the foundation soil and forming highly hazardous score holes. Elevated groundwater tables generate strong buoyancy uplift forces capable of physically lifting and displacing buried storage tanks. That is the buoyancy uplift. Simultaneously, subgrade saturation causes a weight strength reduction, severely lowering the load bearing capacity of roads and precipitating sudden structural collapse. So, with reference to the road point of view, or with reference to the embankment point of view, material must have to be stable and compacted. Otherwise, it will be get weakened, so that the actual infrastructure may get collapse or degrade. So, material quality must have to satisfy the requirement for the construction activity. Now, topographical point of view or sediment point of view, erosion and sedimentation dynamics. Most important point, where velocity determines carrying capacity and declaration causes deposition. So the geohazard of flooding is tightly coupled with erosion and sedimentation dynamics, where flow velocity determines the total carrying capacity of water. High velocity flood flows transport massive sediment from one location to another location in the form of fine silt, clay, large or heavy gravel particles through the drainage networks, or we can say that rivers or streams. When a flow velocity drops, it induces a distinct sedimentation sequence, depositing particles in a graded bedding planes which forms a sedimentation. This deposition clogs urban pipes and drainage conduits, reducing their cross-sectional capacity of water consumption or flowing and compounding the risk of subsequent flood damage or event. The floodplain concept and the risk based zoning. So why we have to monitor the risk, or why we have to define the risk in terms of zone? So basically the whole cross section of channel is divided into two part: flood fringe and floodway on the both side. So main channel is in the between the floodway. After floodway there is a flood fringe. So high velocity and no construction is required in between that channel. After that, 100-year flood inundation and flood proofing required for that channel, where continuous water comes in contact with the topographical features. After that, flood fringe is there. That flood fringe may comes in contact through the flowing water in the rainy season only. After that, it will be a dry phase, and at the end, standard project flood limit we have to design. So return period is most important point to monitor the floodplain concept or the zoning the risk, where 100-year flood is not equal to one every 100 year. So the flood is occurred before 100 year is not constant, it will become in 100 year only. So return period is an event with 1% probability of occurring in any given year, so in any upcoming years. So the civil engineers evaluate these zones using return periods, most notably the standard of 100-year flood metric. The floodplain is divided into the central floodway, which handles high velocity flows, the flood fringe, where flood proofing is strictly required. Now, moving towards the mitigation strategy, the hierarchy of controls. The hierarchy is dependent on avoidance, resistance, resilience. Avoidance is dependent on the non-structural things. Resistance is dependent on the structural things. Resilience is dependent on non-structural things. So mitigation flood geohazards relies on a established engineering hierarchy of controls categorized into structural and non-structural measures. The top tier is avoidance, a non-structural strategy focusing on land use planning to completely keep human populations away from the high risk waters. The second tier is resistance, where utilizing structural elements like dams and levees to physically block water from entering developed zones. The final tier is a resilience, incorporating non-structural adaptations like building codes and warning systems to minimize damage when water is in heavy quantity. The structural mitigation measures conclude that the dam reservoirs, embankment levees, channelization, three stages. So in dam and reservoir, peak flow storage is there. Embankments and levees, lateral confinement is there. Channelization, velocity and enhancement is there. So with reference to that diagram, the Phreatic line shows that the theoretical line above which the soil is unsaturated and below which the soil is saturated, showing water seepage. Means in upstream side the water is stored, that whole water may get percolated or may get seepage through that earthen dam wall. So with reference to that earthen dam wall, the Phreatic line is the marcation, or we can say that the marking. Below to that the soil is saturated, showing water seepage, and above that the soil is unsaturated. Okay, So the structural mitigation directly manipulates the hydraulic regime through three main methods: peak flow storage, lateral confinement, and velocity enhancement. The dams and reservoirs store peak flood waters to release them safely over time, while channelization alters channels to enhance flow velocity. Levees and embankments provide lateral confinement containing river channels through specialized multi-layered geotechnical barriers. Engineers must have to design these all embankments with impermeable clay cores. That is, we required huge compaction and riprap protection, or we can say that the strong wall, while monitoring the Phreatic seepage line to prevent piping failure. Non-structural mitigation measures. Previously we see the structural mitigation measures. Now we see the non-structural mitigation measures. That is, we can say that adaptation. That is, we can say that adaptation, which is have the role of reduce vulnerability without altering the hydraulic regime. So we didn't have to change the hydraulic regime or channel, but we have to reduce the vulnerability activity. So non-structural measures aim to successfully reduce community vulnerability without altering the natural hydraulic regime of a water body. Early warning systems utilize remote telemetry and radar stations to detect upstream precipitation and provide life-saving evacuation time. Floodplain zoning acts as a regulatory tool. Floodplain zoning acts as a regulatory tool to legally prevent structural development inside high velocity floodways. Structural flood proofing elevates individual houses, while insurance mechanisms act to transfer residential financial risk. At the last, the case study, or we can say that a forensic case study, system failure. So Mumbai 2005 and Kerala 2018. Failure mode, drainage with reference to the Mumbai capacity versus high tide. Huge amount of rainfall, 944 mm within 24 hours. So capacity is only 25 minimum per hour, but rainfall is occurred 944 mm within 24 hours. Result, outlet blocks by tide. In Kerala 2018, failure mode is reservoir operation. Issue is the dam full prior to rainfall. Result, emergency release compounded natural flood. So basically, the emergency flood gauge releases compounded natural reservoir flows downstream the systematic infrastructure destruction. So in 2005, Mumbai flood occurred an extreme 944 mm rainfall in between just 24 hours. So forensic analysis of historical disasters reveals how combined natural triggers and engineering failures produce catastrophic geohazards. Stay tuned guys. Happy learning.